So a little bit more on like who am I? You can find me on Medium. I wrote a number of posts related to performance. These are some of the kind of more interesting ones. Then I'm also the creator of ActualChat. You can try the app, and my previous talk on Fusion was covering a decent amount of code from ActualChat. So I definitely recommend you to play with it to see the technologies we are going to talk about in this talk. Yeah, that's a screenshot. Okay, but ultimately it's about Fusion and its RPC protocol, which you can use independently from Fusion, so you don't need Fusion to use ActualLab.Rpc. So just a kind of reminder, right, what Fusion is. It's a distributed real-time state management abstraction that's extremely powerful by itself, but its distributed part is powered by the protocol that is built in particular to address some of the problems other or more, let's say, standard protocols don't address or can't address well. And here I'm going to talk mostly right now, at least I'm going to explain why. So that's so a bit of a history. A long time ago, like 1 year ago, actually, a little bit more than 1 year ago, Fusion was relying on HTTP. And HTTP works like this, right? You have a client, which, when it has to get some data from the server, it sends the call. It's like one message, right? And gets the response back. So all of this stuff, HTTP is a text-based protocol on top of TCP/IP, and that's nearly it. So for Fusion to make it work for Fusion, I've built kind of extension to this protocol on top of this protocol. Basically, when Fusion sends the call, it sends a special header, and when a web server replies, it responds with another header if it sees this one. And basically the value it gets in this header allows it's basically the ID of publication on the server side. And if you watch messages on the WebSocket channel, basically you can think of it as a side channel for invalidations, right? Fusion watches for these messages. So basically it kind of establishes this channel in background and watches for the messages there, and the computed values it creates on the client, it also invalidates them when it sees the invalidation message here, right? All of this seems pretty weird if you don't know much about Fusion, but nevertheless, if you know about Fusion, then this is how to say, basically all of this is very logical, right? It needs one other message to indicate that certain value is kind of expired or stale or invalidated, and that's how it gets this message. Now, I guess why? What else this protocol allows is, if your client is smart and it knows that when you send certain requests, for example, first time you send the request for session 1, get user, and gets the data, right? And invalidation message for it didn't came through yet, or like it just wasn't invalidated. Then when you send the same, or like when the client gets a request to execute the same call for the second time, and it knows for sure that it's the same value, right? The one you got, because invalidation message didn't came, and it returns it. So that's like what kind of Fusion does in general, and it's like one of its key features. It eliminates like tons of calls. It's about networking calls. It's about remote computation or like local computations. It does it in the same way, like nearly like is described here, right? So. And yeah, that's how like all of this actually looks in terms of what it adds to the protocol. So basically, uh, uh, the response has some extra headers, request has some extra headers. But what I want you to pay attention to is the amount of data transferred here. Well, or like, I think there was a bunch of problems actually with the specific implementation. I think first is that so we were using all of this in actual chat, and the amount of traffic you get if you use HTTP, it's way higher than we want to have. So ideally, you want to use more compact protocol, right? And the second piece is like this stuff with side WebSocket channel and like primary sort of communication channel. It was extremely difficult to kind of make it work right, in the sense that like imagine a mobile app, right? And you are in the car and disconnect happens like each and every time. So for HTTP, like you send the message, and it's like if you know how HTTP works, then like you get a timeout. You may get a timeout way after like you send the call, right? So basically, at some point, it detects that like, okay, you are disconnected, but it's not immediate, right? Then like it's different with your WebSocket channel, with your regular messages. So basically, it's a mess, and uh, I think that was like ultimately the main reason to build like our own protocol for um, um, well communication, which is extendable enough to support this kind of 1+2 transmission model that Fusion needs. So that's one of slides from my old presentation about Fusion. Basically, it compares, like kind of like not quite compares, but mentions that I long time ago I wanted to implement a more efficient protocol for Fusion specifically, but like so the kind of the special ability that Fusion has is it eliminates network calls, right? And like no other protocol has it. So that's why I think Fusion was kind of more interesting choice than, for example, gRPC even before all of that. But like, so all of this changed nearly a year ago. And yeah, that's just kind of, so you probably already understand how it works with Fusion. So it, yeah, sends request, gets a response, and maybe at some point later gets an invalidation or doesn't. And it also supports like caching, like with you can think of this scheme as ETAG scheme, but like it implements it for like any calls you make. So yeah, back to kind of now, and we already so we have this protocol ActualLab.Rpc, which is incredibly fast. And here is like, well, here are some highlights. So first of all, in terms of calls, well, per single core, your server can process around 350,000 calls per second per core. It's an extremely high number. If you look, for example, at like well-known gRPC benchmarks, you will notice that you see the same number, but for maybe 4 cores. For streaming, yeah, it supports streaming. It's about 5 million items per second, and that's completely crazy number, because like normally you need, well, I'll show you soon like how big these numbers are actually compared to other protocols. So how large these numbers. And besides that, it's also extremely convenient if you use it on .NET, and by the way, it doesn't work anywhere else. So it's, if you are building everything on .NET and your client is on .NET, or like your cluster of servers is all on .NET, and that's like an extremely basically good fit. But otherwise, like you, well, I mean, no one prevents you from using other protocols. It's just like this thing works only on .NET. So it's extremely convenient. Basically, all you need to use it is a shared interface between client and server. You don't need to put any attributes or like whatever. All you need is to like properly register the client or the server. So it's about service registration. It supports streams. I mentioned it already. Moreover, like it supports streams better than anyone else. It can, I mean, you can send streams with items containing streams, and like can send them as arguments to calls, as part of arguments to certain calls, as part of results, and so on. So basically, it's like a fully native citizen there, or a fully native data type there. Well, it also supports one-way calls. These are the calls you send and don't expect to get the result back, and it's not going to be sent. So it's like no response calls, or like they're called RPC no wait calls in RPC. It's interesting that like in reality these calls are used by the protocol to deliver back the results, and so basically all the system level stuff that happens, it's kind of powered by these calls. There's a system service that runs on like on kind of, I mean, available as a server on the client and on the server side, and basically regular calls happen because these two things, they exchange with system messages, which are one-way calls. Okay, and one interesting thing is that the protocol is fully bidirectional, which means that the server can call the client once it connects. So it's not like just the client can call the server. You can do the opposite as well. And it also supports extremely flexible routing, in the sense that when you send the call, the destination, I mean the server that will process the call, it's determined not like in advance, but right when you send the call. So basically, a single like client can route calls to like hundreds of servers, and all of this happens transparently. Finally, so unsurprisingly, it uses the fastest serializers available on .NET, memory pack, message pack, and yeah, custom serializers are also supported, JSON, of course, as well. And it's AOT friendly, which means, well, I mean, you can use it on you can use it in Maui. You can use it, well, literally anywhere where you probably don't want to run full-blown .NET. There is a bunch of interesting features. For example, transparent reconnection. It's like, I mean, typically, right, if the server is unavailable, then like your call will fail. So with RPC, it's never like this. The call will fail only when you cancel it explicitly by canceling the cancellation token. So at least that's what happens by default. You can override these for certain calls and stuff like this, but by default, it doesn't cancel any calls. And like it basically will be trying to send it and process it until the moment you cancel it. So once connection, so if you are not connected right now, then the call is going to it's going to be running, let's say. So the whoever sent it is not going to get the result until the connection is established and like the call is executed and the result comes through back. Okay. And overall, this is an extremely good, I mean, this alone is like a solution to so many problems. You basically don't need to care of this reconnection thing, or like you don't need to worry about broken connections and stuff like this. So the processing of all of this stuff is kind of baked into the client and the protocol, and it runs on top of WebSockets. Okay, so yeah, how efficient this thing is, and this is I think what you need to pay attention here is this part, the yellow kind of bucket of numbers. You see that probably it's like 2 kilobytes or so, right, for a pretty tiny number of calls. And if we look at similar kind of scenario here, it also sends, I think, I don't know, like 5 or 6 calls. And so first 2 are handshakes. So it's like it happens just once. But the rest, I think it's, how much? Well, my guess is like 400 bytes, right? 5 times less. That's nearly the same set of data is transmitted. And so it's basically way more efficient than HTTP, of course. And interestingly, that like, yeah, if we turn on other Fusion features like local caching, then it's going to be even, well, in terms of data more, but in terms of number of transmissions, like all the calls are sent as a single packet and you get a single response back. So it's extremely efficient. Okay, now we are going to benchmarks, and let's remember a single number: 120,000 calls per second. Any Redis instance, or like at least okay, like default Docker container for Redis has Redis benchmark tool, which can benchmark Redis. So that's the number of calls Redis instance can process per second on my machine. It's unconstrained, right? And like basically it sends them in parallel and stuff like this. And so that's the number of calls that's kind of presumed to be normal for high performance service, right? Okay, now I'm going to run RPC benchmark, and that's a benchmark that, like, sorry, you can run it on your own. I'll run its Dockerized version. Oh, let's run it for calls, right? So it's going to, okay, cool. It's already built in my case. So what's interesting here, the server in this benchmark is constrained to 4 cores, and you can compare some results from this benchmark with gRPC benchmark. I think there is one. I so I'll add the link in the end. But one of tests here is directly comparable with gRPC benchmark. And but what also worth mentioning is that well, it actually benchmarks gRPC on .NET, and so this thing is capable of benchmarking nearly every, at least kind of every well-known RPC protocol on .NET. So right now it runs kind of a little bit slower than it's supposed to run because, well, of this video recording and like processing. So it's not exactly the result that you or that's kind of the best on my machine, but nevertheless. So instead of like waiting here, I guess I'll run a video with all of these benchmarks recorded. Yeah, I think the speed up is like 30x or 20x here, and that's basically it shows what you are supposed to see if you run these benchmarks locally. So sorry, some are in Docker, some are just running locally. So the Docker version is constrained to 4 cores. Remember this. Okay, so that's like what you are supposed to see, but with decent speed up. Yeah, so I'm not going to wait till the very end here. I'll just show later that these numbers are nearly the same in my slides. Okay, so let's get back to, well, 2 slides, right? So remember, Redis 120,000 calls per second. So what actual RPC does with 4 core server? It's around, well, 1,250,000 calls per second. I think the most recent version even does a little bit more. And by the way, speaking of the call, you can compare with other benchmarks. So say hello scenario is the one you can compare with gRPC benchmark on like every, I mean, there is an implementation of basically this thing for every platform, and you can directly compare the results here. But overall, ActualLab.Rpc is like 2 to maybe 4x faster than gRPC on calls, and probably like, again, well, it's I don't know, 1.5 to 2x faster than SignalR. As for streams, the difference is even bigger. I think it's 3x faster than gRPC on streams with short, like with small items. And well, I mean, why small items and why it's important is, well, we measure the extra expenses that framework adds, right, or like library adds. So the smaller is the item, the more kind of complex is the scenario. It basically highlights the cost of kind of processing the stream item by the library. So that's why. So stream 1 is like, I think, extremely short items. Probably, I mean, the array they sent is 1 byte array, but the item itself, so basically there's some envelope as well, but it's small. And stream 100 is 100 byte items. So, but even on 100 byte items, the difference is pretty huge with gRPC. And again, that's on Docker. So it's like a server constrained to 4 cores. That's how much it can process. Now, if we run the same tests just without Docker and unconstrained, and on my machine, which is Ryzen, well, this Ryzen. So for calls, and remember the client and server both are running on this machine, so it's like nearly, I mean, you can get twice of that if you run just server. So it's, I think, 6.5 million calls currently at peak for the kind of small calls. And as for the larger ones, well, it's still basically uh, about 4 million calls. And yeah, this result here, it's an exception. Basically, there is a lock contention in concurrent queue with memory pack, but there is no such problem with message pack. So it's basically like, I think they hit some weird scenario where for this specific payload, serialization is much slower somehow. But yeah, so it's not related to RPC protocol, it's related to memory pack and like ultimately concurrent queue on .NET. And here is the chart for streaming. So as you can see, the server here sends, I think, about 70 million calls per second. I mean, server plus client on the same machine. So why it's fast? Uh, well, I think the key piece is automatic batching, and it's also based on the fact it uses channel of RPC messages. So basically, a low-level abstraction that kind of sends and receives call is channel of RPC messages. And channels are extremely efficient and powerful thing on .NET. If you never use them, then like, you should learn about them. But like basically, they allow you to create really nice pipelines. So automatic batching is basically a piece of code that awaits new messages on a channel, and while it can get these messages synchronously, it packs them into a single networking packet. And or like when it hits a certain size threshold, but like this piece is even customizable actually. And why this thing is important is like, well, the less awaits you have, the more efficient your pipeline is. So like basically the more you can pack into a single packet, the better. It's not better just in terms of networking, but like also in terms of the extras you kind of spend on the receiving end, right? There is also one nice unification. Everything that like the protocol can actually deal with is a call. Just well, some calls are one-way calls. They don't require a response, and that's how RPC sends a response to regular calls. Like basically, it sends a call to one direction and gets back a message called like system.ok. I mean, that's the name of the method, or system.error, which delivers the result of this call. So the unification, of course, helps to build a simpler pipeline. And instead of like dealing with, I don't know, like tons of different messages, it has just one. So that's why it's kind of cool piece. And one other important thing is that, like, yeah, it uses the fastest serializers available on .NET, all thanks to Yoshifumi Kawai. If you don't know who is this guy, well, you definitely should read about, well, both these two serializers and the person. But it's interesting that like two fastest binary serializers on .NET are implemented by the same person. Um, so yeah, besides that, there is a fancy argument list type, which is basically a type that efficiently wraps method call arguments without boxing, or like with just one allocation. So it's like, for example, if you look at how Signalar or like other RPC libraries process something similar, they allocate they box every argument, and the argument list is exactly what kind of allows to skip on boxing. Uh, there are special paths eliminating some memory copies in case the amount of data to copy is relatively large, and even some like really kind of low level optimizations on the protocol, or like sorry, on serialization format level. You can optionally turn them on, and for example, it can send method name hashes instead of method names. And it kind of seems stupid because you can get hash collisions, right? But like in reality, the chance of collision is just like 1/100%. So it's like 1 per 10,000 if you have 1,000 methods. So it's very low, and it makes sense to use it if you actually need the peak throughput, right? And finally, the last piece is the proxies that ActualLab.Rpc uses. Interestingly, the proxy generator and the proxy code that is used by ActualLab.Rpc is the same. These are the same proxies as Fusion uses, which means that these proxies are generic. Generic in sense that like they can intercept any calls. So it's basically like they are generated once, and you can reconfigure them to do different kind of processing dependently on what kind of interceptor you plug in. It's kind of similar to Castle Dynamic Proxy, but the difference is that, well, first of all, it's 2x faster because the number of allocations is way lower here, and I'll show you that. And it's like literally a single allocation per intercepted call. And the second piece is that these proxies are generated in compile time, not in the runtime. And because of that, it's AOT friendly. There are some other optimizations, like, for example, this argument list type has special paths for cancellation token access. And like special because otherwise there would be a virtual generic call or boxing. So so there is a decent number of such optimizations that kind of eliminate the most kind of frequent wastes, let's say. Okay, let me show you the proxy code, right? And that's a benchmark. You can find it in Fusion repository. Probably wouldn't. So basically, it's like one of tests in Fusion repository. But you can see that, like, what's interesting here is that, for example, for this call, right? First of all, ActualLab.interception interceptor, or like proxies, they process these calls 2x faster than Castle Dynamic Proxy. So 2x plus, I would say. But another interesting piece is that like they allocate just 32 bytes per call. Well, this is literally like an object header, 16 bytes on 64-bit platform plus like 16 more bytes. That's probably for the arguments here, right? And that's literally it. And as for Castle Dynamic Proxy, as I said, like basically it boxes every argument. That's why there is way more of like way more data is allocated on the heap. Like I think in this case it should be at least 4 allocations per call. Okay, and yeah, so you can, I guess, walk through like you can do this. I mean, you can put a breakpoint into, I think, every call chain involving Fusion or RPC, and you will see something like this here. At some point, you will see the interceptors on the call stack and the proxy on the call stack. So, and I'm let me quickly show you a proxy code here, like why it basically explains why it's so efficient. So this first part happens just once because of these two question marks equals, and like what happens here is it caches the delegate that may call a base method or like the actual proxy target. It has to be here because if it calls the base method, like it literally has to be here, right? You can't kind of call base from base method from the random spot. But like, so this piece happens just on the first call. As for the rest, so I zoom out a little bit, but as for the rest, like what happens is it constructs invocation, which is a struct. Here there is a single allocation that's kind of that actually happens, and yeah, passes intercepted delegator so that you can call, like your interceptor can call base method, basically the method that is intercepted, right? And uses this weird thing to actually invoke an interceptor. The reason why it uses this weird thing is that, like, so in reality, uh, it calls this method with well, the sorry, so it calls cached intercepted one here, right? And if you look at what cached intercepted one, it's an interceptor.intercept method, but with parameterized with this generic parameter. So basically, like it caches the you may think of this as it caches the delegate that points to an instance of generic method with specific parameters like the return type here. So, and yeah, that also allows this thing to kind of get rid of some allocations. So that's nearly how it works. Oh, and yeah, the other interesting part is that it generates a kind of module initializer for every proxy, which does, in reality, it does nothing because like this method, it actually doesn't call this thing. But nevertheless, the compiler thinks that all these methods are invoked, and basically this is something that allows you to well, first of all, it kind of marks everything that's supposed to be used by AOT, but also it allows you to kind of extend this thing because, well, some types that are used here are interfaces, and if you implement them, like it's going to think that, like, okay, every implementation with every implementation of the interface is supposed to be used with like certain method parameters and methods. So that's why that's what kind of makes this thing AOT friendly as well. Well, and yeah, finally, I think like it caches nearly everything that's possible to cache, so that when it processes the call both on sending side or on the receiving side, it doesn't do any work that actually shouldn't be done. Okay, now it's demo time, and that's going to be the very first demo here. Or maybe I'll start from, well, more visually attractive one. It's one of Fusion demos, but I think the interesting part here is this one. So it's basically, it uses RPC streaming. So Fusion is not used here, or at least like this part shows just the RPC piece, and yeah, it shows that like it basically can send well a stream of images with well nearly the origin FPS, and yeah, it's WebAssembly. Okay, nevertheless, let's run the sample that uh, actually shows the RPC in action. I'll close. Oh, well, we can leave it. If you saw my previous video, you already saw this sample, but I didn't show this part, right? So this part shows just the RPC calls, and you can see that if you refresh the page, then like basically it's stream of rows with stream of items. You can switch it to server, by the way. So there is no any RPC. It just shows that okay, these streams also work locally. I think the only thing that doesn't work is like this ping pong with one-way calls. So okay, so let me show you a couple things here. First, what happens over the network, right? In this case, so you can see that it sends actually like pretty big messages sometimes, which pack a bunch of calls, and so streaming is extremely efficient. It's yeah, it tries to pack as many stream items into a single batch and like multiple items from multiple streams into a single network transmission. So in terms of traffic, it's extremely efficient. The like I think the only way I can scroll so that what's happening right now is like this ping pong stuff, and these are one-way calls, and basically like 32 bytes and 42 bytes response. I think most of this stuff is like at least large part of this stuff is the message itself. Okay, so let's look at the code, I guess, right? And see. So yeah, let's start from the client. So I think everything that happens here happens in initialize async. Oh, by the way, let me show you one other thing. So it's interesting, right? How it's going to behave if we shut down the server right now, and we'll go to the same page, right? So I stop the server. So you know that this stuff works even if you are disconnected. Kind of works, render stuff, because I mean I can still kind of scroll through these pages even if you are disconnected, because there is an offline cache. But like if we go here, it doesn't show anything, right? And like reconnecting. So will it work if I'm going to start the server, right? Yeah, I'm curious. It's supposed to work. So you see that like basically as soon as it connected, it like started to show the data. And if you again stop it, and like okay, it tries to send pings, but doesn't get pong back. So that's what happens. Let me kind of click a bunch of times here to make this counter count for at least like 30 seconds or so. Okay, so now it's going to take a while for it to reconnect. So again, I'm running the server right now, and let's get to some other page. You see that the counter is like the same, but now if, yeah, so it's not connected. That's why basically it can like run all these calls in initialize async, they are waiting. And if I click reconnect, then like things start to spin. Okay, so let's look at the code here, right? Yeah, we need this page to be disposable, because that's what you have to do if you, of course, deal with streams and want to kind of shut them down gracefully. So what we do here, we send greet call and we send get table call, and also start ping pong task. Let's start from this thing, right? So greet is a simple call returning string, yes, string. And if we go to the implementation, then like that's the result it produces on the server side. So nothing fancy. Once greeting task is completed, it sets greeting, right? It's interesting. Well, I mean, we could put something like state has changed here, right? But it waits for everything before rendering basically this thing. But so the point is then like it also sends get table call and ping pong task starts ping pong task. So let's look at get table. It returns table of int. What is table? Table is actually a table of t here. So it's an instance of generic type, and it has a title and RPC stream of row of t, right? And row of t has an index and RPC stream of items. So as you might guess, this thing can travel over the RPC protocol, and you can use it as part of other objects and as part of arguments like here, and deeply inside some other objects. And like, yeah, you can send stream items which contain other streams. So let's look on like, so here we get the table, right? And then create a model and also start read table method. So what read table does, it literally iterates through its rows and adds the row. Then for every row it calls read row. And if you look at the read row, it's kind of even more interesting, right? It basically iterates through items and puts them into the model, but like in the end, it calls, like when it basically gets the next item, it calls update sum, and update sum gets the row and creates an RPC stream out of its items and sends the call to some method which gets this stream. So basically, like the point is like this sample shows all kinds of streaming you can get. And finally, the ping pong part, it's the unusual thing here is that like the calls that it sends are one-way calls. So that's why we so this check, it's just like it can't work, of course, if there is no RPC. But like we start send pings task here, and then on the there is a so client-side service is basically the service that registers calls to pongs, and it exposes these like results in pong channel. But I think that's the only interesting part here. It's if we go to send pings, then like we get peer. So for one-way call, you can you have to pre-route most of them, and that's why we get the peer. And uh, oh no, sorry, you don't have to. You like yeah, you don't have to. But like if you, for example, respond to such calls on server side, and you need to know the peer that kind of send you the ping to respond. But here we just await for like when this peer gets connected, because like these calls, they are kind of fire and forget, and if you are not connected, then it's just going to be kind of skipped. So we call this method in the end, simple service.ping, pass a message. And if you look at the signature, the important part here is that there is RPC no wait. So basically, it's a method that returns a task of RPC no wait. When you see such a method, it indicates for RPC that it's a call that doesn't expect, like you don't have to send a response to such a call. Okay, and that's why you also typically don't need to have a cancellation token there. I mean, like these calls, they are sent like almost synchronously. So they enter that kind of send channel like synchronously. So let's look at the server side, right? So it's pretty easy. So get rows, I think it should return the async enumerable of rows, right? And all we need to do is to kind of rewrap this stuff into RPC stream to make it work. So basically, RPC stream is a wrapper over async enumerable. The reason why you can't pass just async enumerable, like simply async enumerable, is that for most of serializers, there is no way to like override the serialization for this type, but there is an easy way to override serialization for your custom type. That's why there is a wrapper RPC stream. Well, plus it actually provides you with a few useful properties. So for example, these two, ACK period and acknowledgement period and acknowledgement advance. It basically tells you how, like you can customize it on per stream basis. Okay, so for streaming, I think it's more or less clear, right? It's like you, you literally like deal almost with the async enumerables, but with streams. So one thing you need to remember is that like on the client side, the stream can be enumerated just once. You can't enumerate it multiple times. Okay, so and for get rows, so you basically you see that like every time it needs to send a stream, it constructs it from async enumerable or regular enumerable. Okay, and I think the only tricky part here is ping method. It's like it has to respond with pong. So the way it responds with pong to the same peer, it gets the inbound RPC context and gets the peer here. Then it creates outbound RPC context and activates it. So inside this using block, basically, the outbound RPC context is kind of pre-created. And so since it passes the peer there, by default, so if you don't do that, then RPC will use its router to find the peer. And that's what happens normally. But in this case, we want to send a response to the same peer that like got this call, right? I mean, from which we got here. So that's why we kind of pre-route the call we are going to send. And other than that, that's it. So okay. Yeah, I'm not sure. Like, I guess it's more or less clear. I think what I want to show is like you can use RPC without Fusion. All you need to do is nearly this. So first you add RPC, then you do this, and so we don't, of course, like we can't expose Fusion clients, but like we can expose RPC clients. So, and in this case, so we literally, like that's literally all you need to do to configure RPC on the client side. You add the RPC. It's the same, by the way, on the server side as well. And then you, tell that you're going to use WebSocket client for this RPC protocol, and like you add the client for this service, and basically that's what ensures that you will be able to use it. It's proxy in, like, you will be resolved basically this service. Okay, that's mostly it, I think, for the RPC. Did I change something? Oh, okay. Okay. Well, let me think about what else is like worth mentioning here. Oh, the last part, and I guess it's going to be the most weird one and also the fun one. So there is a demo called MeshRpc. And it shows that, like, well, let me find one RPC helpers route call. So, find usages. So, you can, so RPC call router is a delegate, and you can register your custom one. So default one routes every call to the default peer, default client peer. But you can register your own call router, and if you look at the code here, basically you will see that this method gets an RPC method def, the method that was called on the client, and all of its arguments, right? And it needs to return peer ref in the end. This thing, that's I think of it as a URL, but more flexible. So basically, it's like a custom URL with custom scheme, something like this. So you see that this thing basically gets the type of the first argument, checks if it's host ref. So it's like if the first argument of a call is an exact reference to specific host, then it's going to return a special ref that is a host ref. I mean, basically it will construct a reference to a peer that is kind of associated with specific host. Then there is a more complex thing that, like if it sees a shard ref, then it returns basically a ref to a shard. And the difference is that, like, I mean, if you implement dynamic sharding when hosts join and like leave shards, right, then a single shard may resolve to one host first, like at some point in time, right, then to another host, and so on. So basically, it's a dynamic thing, right? And that's why there is another peer ref that's more complex. You, by the way, can see that they are implemented right here. So as part of this demo, you basically can find all the source code that you need. So, and anyway, and let's say if it sees that the first argument is integer, then like in reality, it gets this integer, construct a shard reference to a shard that can be associated with this integer. And so basically, like it's fully dynamic routing. And let me find MeshRpc here, right? So when you run this sample, and that's not it actually. So there is more here. But so I'll pause it at some point and show you what's going on. So basically, it simulates a situation when hosts are starting, dying, and join basically some map of shards. And so plus here indicates that like this host with this name, like virtual host, but it's like real server here. I mean, real ASP.NET server with ActualLab.Rpc. So it took shard number 1, 3, and like I don't know what this number is, and the scheme changes, right? And so what it does, it is like if you scroll here, you will see that like it sends calls to like basically so like sorry. So the service on each of these hosts, it basically tries to communicate with other hosts, and they maintain this map of shards independently and like basically communicate independently. And so the whole point of this demo is that like there should be no red lines showing that some calls like failed in a hard way without reprocessing and stuff like this. And yeah, that's what happens here. I mean, I can stop like, and by the way, it calls fusion services, non-fusion services, and like basically it shows that the protocol is extremely tolerant to different kind of failures. So that's nearly it. You see that like right now it kind of throws these calls very rapidly. Okay. So that's what ActualLab.Rpc is. So this part with routing and so on, it's kind of complicated, and you really need it only if you want to have a mesh of services on the server side. And like I think the problem it solves like ultimately is that like you really don't need a load balancer with it, and this kind of also allows you to implement a more efficient communication schema, but on your server side. Plus, yeah, it's extremely, how to say, well, basically the error reprocessing, like connection problems and so on, they are kind of out of scope because of the protocol and the library. Okay, back to slides, right? That's not the slide. So, yeah, I already shown you this demo. And yeah, it's just a reminder that if you use it together with Fusion, you get like the numbers that are completely out of reach, even with RPC itself. So it's a very different story if you use it with Fusion. So, and just a reminder, right? We started from, I think, or like not started, but there was a slide showing how many calls Redis can process. If you think about these calls, these are extremely lightweight in terms of processing, right? So it's basically like kind of dictionary lookups. So I think I would say that the networking part in this case should be kind of more expensive than the rest. Nevertheless, so just 120,000 right calls per second, and so here you see numbers like, well, I mean, these are kind of heavy calls, so just 1.5 million calls per second, but yeah, more lightweight calls, similar to probably the test on Redis, are, well, 6 million calls per second on this machine. Okay, it's like 60x, like 50x compared to Redis. So yeah, that's where you can find ActualLab.Rpc samples. And thanks a lot for watching. Please feel free to reach me out, ask any questions, and yeah, if you would like to contribute something, then that would be amazing. Okay, thank you.